45 years ago, two robotic explorers launched from Earth, carrying humanity's hopes into the cosmic unknown. These twin spacecraft would travel farther than any human-made object before them, revealing worlds so alien they defied every prediction scientists had made. We'll witness a moon that spits fire into space, rings that sing like cosmic wind chimes, and storms that could swallow our entire planet whole. We'll discover oceans hidden beneath miles of ice, winds that race at impossible speeds, and the very edge of our solar system itself. Prepare yourselves. Voyager 1 approached Jupiter in March 1979. Its cameras focusing on a swirling red oval that astronomers had watched through telescopes for over 300 years. But nothing could have prepared scientists for what they were about to discover about this mysterious crimson mark floating in Jupiter's atmosphere. The Great Red Spot wasn't just a storm. It was a hurricane so massive that you could drop Earth inside it twice and still have room left over. As Voyager's instruments peered into this cosmic cyclone, they revealed wind speeds reaching 400 miles per hour. Fast enough to circle our entire planet in just 6 hours. The storm's red color came from phosphorus compounds being churned up from deep within Jupiter's atmosphere, like cosmic blood rising to the surface. What shocked scientists most was the storm's age and stability. While hurricanes on Earth last for days or weeks before burning out, this Jovian monster had been raging for centuries without losing strength. Think of it like a spinning top that never stops, powered by Jupiter's internal heat and the planet's rapid rotation. The storm rotates counterclockwise, completing one full rotation every 6 Earth days, moving like a giant cosmic gear in Jupiter's atmospheric machine. Voyager's close-up images revealed intricate details within the storm that no telescope could capture. Smaller storms swirled around the Great Red Spot's edges like cosmic remoras following a whale, sometimes getting absorbed into the larger system. The storm's eye measured 12,000 miles across, wide enough to swallow our moon with room to spare. Temperature readings showed the storm's center was actually colder than the surrounding atmosphere, creating a high-pressure system that acts like an atmospheric mountain floating in Jupiter's sky. But the most mind-bending discovery was yet to come. Scientists realized the Great Red Spot was actually shrinking. Historical observation showed it had been twice its current size just 100 years earlier. This cosmic hurricane was slowly dying, though it would likely survive for centuries more before finally disappearing into Jupiter's turbulent atmosphere. The storm's behavior defied everything meteorologists knew about weather systems. On Earth, hurricanes weaken when they move over land or cold water. But Jupiter has no solid surface to disrupt the flow. The Great Red Spot floats in an endless ocean of gas, drawing energy from the planet's core heat 400 million miles from the warming influence of our sun. As Voyager 1 transmitted these incredible images back to Earth, taking 18 months for the radio signals to reach mission control, scientists realized they were witnessing something unprecedented in human history. They were watching weather on an alien world, seeing storms that operated by rules completely different from anything in Earth's atmosphere. Just days after Voyager 1 revealed Jupiter's secrets, it turned its cameras toward the planet's moons and discovered something that made every scientist on Earth question the laws of physics. Io, Jupiter's innermost large moon, was literally exploding before their eyes. Navigation engineer Linda Morabito was examining images for navigation purposes when she spotted something impossible, a crescent-shaped plume rising 300 miles above Io's surface. At first, mission controllers thought they were seeing a background star or a camera malfunction. But as more images arrived, the shocking truth became undeniable. Io was the most volcanically active world in our entire solar system. 8 active volcanic eruptions were visible in that first flyby, shooting sulfur and sulfur dioxide hundreds of miles into space. These weren't the gentle lava flows you might find in Hawaii. These were volcanic explosions so powerful they could launch material completely off the moon and into orbit around Jupiter. Imagine standing on a world where the ground beneath your feet constantly trembles and mountains regularly explode with the force of nuclear weapons. The volcanic plumes created umbrella-shaped clouds that spread across hundreds of miles before falling back to Io's surface like alien snow. Some eruptions reached temperatures of 3,000 degrees Fahrenheit, hot enough to melt copper instantly. The moon's surface changed so rapidly that features visible in one Voyager image had completely disappeared by the time Voyager 2 arrived 4 months later. But what was driving this incredible volcanic activity? Scientists discovered that Io was being constantly squeezed and stretched by Jupiter's immense gravity, like a cosmic stress ball in the hands of a giant. As Io orbits Jupiter, the gravitational pull from Jupiter and its neighboring moons, Europa and Ganymede, creates tidal forces that flex the moon's interior. This constant kneading generates enough heat to keep Io's interior molten, creating a world-sized volcanic furnace. The surface of Io resembled a cosmic pizza, painted in brilliant yellows, oranges, and reds from sulfur compounds. No impact craters were visible anywhere. The constant volcanic activity had erased every scar from space rocks, creating the youngest surface of any solid body in the solar system. Lava lakes bubbled and churned across the landscape, some larger than entire states on Earth. Voyager's instruments detected sulfur dioxide frost covering much of Io's surface, created when volcanic gases freeze in the moon's thin atmosphere. The volcanic plumes weren't just spectacular light shows. They were actively resurfacing the entire moon, burying the landscape under layers of fresh volcanic material every few thousand years. Think of Io as a cosmic construction site where the entire world gets rebuilt over and over again. The discovery of Io's volcanoes proved that moons weren't just dead, airless rocks orbiting their planets. They could be dynamic, evolving worlds with their own weather systems and geological processes. While Io blazed with volcanic fury, its neighbor Europa appeared deceptively calm from Voyager's cameras. This ice-covered moon reflected sunlight like a cosmic mirror, showing a surface smoother than a billiard ball. But hidden beneath that pristine frozen shell lay a secret that would change how scientists searched for life in the universe. Europa's surface revealed a puzzle of cracks and ridges that stretched across its entire frozen landscape like a shattered eggshell. These weren't random fractures. They formed organized patterns that suggested something incredible was happening beneath the ice. The moon's surface showed almost no impact craters, meaning the ice was constantly being renewed and resurfaced by some hidden mechanism. Scientists studying Voyager's data realized they were looking at the frozen surface of a global ocean beneath Europa's ice shell, which could be anywhere from 10 to 15 miles thick. Lay an ocean containing twice as much water as all of Earth's oceans combined. This subsurface sea was kept liquid by the same tidal heating that powered Io's volcanoes. But instead of creating eruptions, the energy warmed a vast underground ocean. The ice shell wasn't static. It was constantly moving and reshaping itself like frozen pack ice on Earth's polar seas. Warm water from below caused the ice to expand and crack, creating the intricate pattern of ridges and valleys that covered Europa's surface. Some areas showed where the ice had pulled apart and refrozen, creating features that look like frozen rivers running across the moon's face. Think of Europa like a cosmic egg, with a shell of ice instead of calcium carbonate. Crack that shell, and you'd find not yolk, but an ocean deeper than any trench on Earth. This ocean was dark and cold, never touched by sunlight, but it was liquid water, the essential ingredient for life as we know it. Scientists began to wonder if this hidden sea might harbor living organisms in its depths. The implications were staggering. If Europa had a global ocean, it meant that habitable environments might exist throughout the outer solar system, far from the warming influence of the sun. Life might not need sunlight and moderate temperatures. It might thrive in the cold, dark depths of alien seas, drawing energy from chemical processes instead of photosynthesis. Voyager's discovery transformed Europa from just another ice-covered rock into one of the most intriguing worlds in our solar system. The smooth, youthful surface suggested the ocean below was actively connected to the surface ice, potentially allowing nutrients and chemicals to cycle between the sea and the frozen shell above. This meant Europa's ocean wasn't just a stagnant pool of water. It was a dynamic system that could support complex chemistry. The search for life beyond Earth had always focused on planets in the habitable zone, where liquid water could exist on the surface. But Europa proved that habitable worlds might be hiding in the most unexpected places, wrapped in ice and orbiting giant planets hundreds of millions of miles from the Sun. When Voyager 1 approached Saturn in November 1980, astronomers thought they understood the planet's rings pretty well. Through telescopes, Saturn appeared to have a few distinct rings separated by dark gaps, like grooves on a cosmic record album. But as Voyager's cameras captured the ring system in unprecedented detail, scientists discovered they had been completely wrong about one of the solar system's most beautiful features. The rings weren't solid bands of material at all. They were made of countless individual chunks of ice and rock, each following its own orbit around Saturn, like a swarm of cosmic bees. Some pieces were as small as snowflakes, others as large as houses, all spinning and tumbling through space in a carefully choreographed gravitational dance that had been playing out for millions of years. What appeared as a few simple rings from Earth actually contained thousands of individual ringlets, each with its own orbital speed and characteristics. The ring system resembled a cosmic phonograph record, with grooves so fine they couldn't be resolved from Earth. Some gaps between rings were caused by tiny moons acting like cosmic shepherds, using their gravity to sweep ring particles into organized lanes. Voyager discovered that Saturn's rings were incredibly thin compared to their vast diameter. While the main ring system stretched over 170,000 miles across nearly half the distance from Earth to the Moon, the rings were typically only about 30 feet thick. Imagine a sheet of paper scaled up to the size of a football field, and you'd get an idea of how remarkably flat Saturn's rings really were. The ice particles in the rings sparkled like diamonds in the sunlight, creating one of the most spectacular sights in the solar system. These weren't dirty chunks of rock. They were mostly pure water ice, probably formed when comets or small moons were torn apart by Saturn's powerful gravity. The largest pieces tumbled slowly as they orbited, creating a gentle cosmic snowstorm that had been falling for eons. But the biggest surprise came when Voyager discovered structures within the rings that seemed to defy physics. Some ringlets appeared braided together like cosmic rope, while others showed dark spokes that rotated with the rings despite having no apparent physical cause. These spokes appeared and disappeared like ghostly shadows moving across the ring plane, created by electromagnetic forces that charged tiny dust particles and lifted them above the main ring structure. Saturn's gravity wasn't the only force shaping the rings. The planet's magnetic field interacted with charged particles, creating waves and disturbances that propagated through the ring system like ripples on a pond. Small moons embedded within the rings carved gaps and maintained sharp edges through gravitational shepherding. while resonances with larger moons created spiral density waves that looked like frozen sonic booms. The ring system was incredibly dynamic, constantly changing as particles collided, stuck together, and broke apart again. What looked like a static, unchanging structure from Earth was actually a bustling ecosystem of ice and rock in constant motion. Scientists realized they were watching the birth and death of ring particles in real time, witnessing processes that had been shaping planetary ring systems for billions of years. Among Saturn's 62 known moons, one stood out as completely unique even before Voyager arrived. Titan, Saturn's largest moon, was shrouded in a thick orange atmosphere that completely hid its surface from view. But when Voyager 1 flew past this mysterious world in November 1980, it discovered something that made scientists question everything they thought they knew about planetary atmospheres. Titan's atmosphere was thicker than Earth's, creating a surface pressure 1.5 times greater than what we experience at sea level. This made Titan the only moon in our solar system with a substantial atmosphere, thick enough for a human to walk around without a pressure suit. Though you'd still need oxygen and protection from the frigid cold, the atmosphere extended hundreds of miles above the surface, creating a hazy orange glow that gave the moon an almost Earth-like appearance from space. But this wasn't an atmosphere made of the familiar nitrogen and oxygen that we breathe. Titan's air was 95% nitrogen with traces of methane, creating a cocktail of gases that produced complex organic chemistry in the upper atmosphere. Sunlight broke apart methane molecules, causing them to recombine into larger organic compounds that fell to the surface like cosmic snow, painting the landscape in orange and brown hydrocarbons. The thick atmosphere created weather patterns that mirrored Earth's in startling ways. Clouds formed and dissipated, winds circulated around the globe, and seasonal changes occurred as Titan orbited Saturn. But instead of water vapor forming clouds, methane evaporated from Titan's surface and condensed in the cold upper atmosphere, creating weather systems based on liquid methane instead of water. Scientists realized they were looking at a world where methane played the same role that water plays on Earth. Methane rain fell from orange clouds, carved river channels across the landscape, and collected in vast lakes near Titan's polar regions. This created a complete hydrological cycle based on hydrocarbons instead of water, the only other world in our solar system known to have liquid flowing on its surface. The atmospheric pressure and composition meant that if you could somehow survive the cold, you could actually fly on Titan using wings strapped to your arms. The thick atmosphere and low gravity, just 14% of Earth's, would make human-powered flight not just possible, but relatively easy. Imagine soaring through orange skies above methane lakes and hydrocarbon dunes. Voyager's infrared instruments detected temperature variations across Titan's surface that suggested diverse geographical features hidden beneath the atmospheric haze. The equatorial regions appeared warmer and likely contained vast dune fields made of organic sand particles, while the polar regions showed the cold signatures of liquid methane and ethane lakes. The organic chemistry happening in Titan's atmosphere created a natural laboratory for studying how complex carbon compounds form and evolve. The moon was essentially a giant chemistry experiment, producing organic molecules that fell to the surface and accumulated over millions of years. Scientists began to wonder if this organic-rich environment might provide clues about how life began on early Earth. Titan's thick atmosphere also protected the surface from space radiation and meteorite impacts, creating a stable environment where complex chemistry could proceed undisturbed for geological timescales. This made Titan a time capsule, preserving conditions that might have existed on early Earth before life began altering our planet's atmosphere. As Voyager 2 approached Saturn in August 1981, mission planners focused most of their attention on the planet's magnificent rings and its mysterious moon, Titan. But a small, icy moon named Enceladus was about to steal the show with a discovery that would revolutionize how scientists thought about life in the outer solar system. Enceladus appeared to be just another boring ice ball, barely 300 miles across and covered in pristine white ice that reflected almost all the sunlight hitting its surface. This tiny moon was so bright it practically glowed in Voyager's images, looking like a cosmic snowball floating in the darkness. But hidden beneath that innocent exterior was one of the most geologically active worlds in the entire solar system. Voyager's cameras revealed that Enceladus had virtually no impact craters on its surface, a clear sign that something was constantly erasing the scars left by space rocks over billions of years. The southern hemisphere showed a complex landscape of ridges, valleys, and smooth plains that looked remarkably young compared to other icy moons. Scientists realized they were looking at a world where geological processes were actively reshaping the surface. But the most incredible discovery came when Voyager detected something unprecedented near Enceladus's south pole. Massive plumes of water vapor and ice particles were erupting from the surface, shooting hundreds of miles into space like cosmic geysers. These weren't gentle puffs of gas, they were powerful eruptions, launching material at speeds of over 800 miles per hour, fast enough to escape the moon's weak gravity entirely. The geysers emerged from a series of parallel cracks near the South Pole that scientists nicknamed tiger stripes because of their distinctive appearance. These fractures were warmer than the surrounding ice, suggesting that liquid water existed just beneath the surface. The erupting material contained not just water ice, but also organic compounds and minerals that could only come from a subsurface ocean. Think of Enceladus like a cosmic pressure cooker with a leaky valve. Tidal heating from Saturn's gravity keeps a global ocean liquid beneath the ice shell, and this water occasionally finds its way to the surface through cracks and fissures. When the pressurized water reaches the vacuum of space, it instantly vaporizes and freezes, creating spectacular ice fountains that feed Saturn's outermost ring. The discovery of liquid water erupting from Enceladus meant that this tiny moon harbored another subsurface ocean, similar to Europa, but with direct access to the surface through the polar geysers. Scientists realized they could potentially sample this alien ocean without ever landing on the moon. They just needed to fly a spacecraft through the erupting plumes and analyze the particles. Temperature measurements showed that the Tiger Stripe region was significantly warmer than it should be based on sunlight alone. Something inside Enceladus was generating heat, keeping the water liquid despite the moon's vast distance from the sun. The tidal forces from Saturn were kneading the moon's interior like cosmic hands working bread dough, generating enough friction to melt ice into a global ocean. The geysers weren't constant. They varied in intensity and sometimes shut off completely before resuming their spectacular displays. This suggested that the underground plumbing system was complex, with chambers and channels that could become blocked or cleared by geological processes. Enceladus was essentially a cosmic version of Yellowstone's geysers, but powered by tidal forces instead of volcanic heat. As Voyager departed the Saturn system, scientists knew they had discovered one of the most promising places to search for life beyond Earth, a small moon with liquid water erupting directly into space. 5 years after leaving Saturn, Voyager 2 approached a world unlike anything else in our solar system. Uranus hung in space like a cosmic bowling ball, rotating on its side with its poles pointing toward and away from the sun instead of spinning upright like every other planet. This bizarre orientation created the strangest seasons imaginable. Each pole experienced 42 years of continuous sunlight, followed by 42 years of complete darkness. When Voyager 2 flew past Uranus in January 1986, it became the first and only spacecraft to visit this distant ice giant. From Earth, Uranus appeared as little more than a bluish-green dot through even the most powerful telescopes. But Voyager's close-up images revealed a world that seemed almost featureless at first glance. A smooth, blue-green sphere with barely any visible clouds or atmospheric disturbances. The planet's unusual color came from methane in its atmosphere, which absorbed red light and reflected blue and green wavelengths back into space. Unlike Jupiter and Saturn, with their swirling bands and dramatic storms, Uranus appeared eerily calm. The lack of atmospheric features puzzled scientists until they realized they were viewing the planet during its most inactive season. Voyager arrived when one of Uranus's poles was pointing almost directly at the sun. But beneath that bland exterior lurked one of the most unusual magnetic fields in the solar system. Instead of aligning with the planet's rotational axis like Earth's magnetic field, Uranus's magnetic field was tilted 59 degrees off-center and didn't even pass through the planet's core. The magnetic field seemed to originate from somewhere deep within the planet's mantle, creating a lopsided magnetic environment that defied all previous models of planetary magnetism. The discovery of Uranus's tilted magnetic field suggested that something catastrophic had happened to this planet in the distant past. Scientists theorized that a massive collision with an Earth-sized object had knocked Uranus onto its side, scrambling its internal structure and creating the bizarre magnetic field configuration. This cosmic collision would have been one of the most violent events in the solar system's history, completely restructuring an entire planet. Voyager also discovered that Uranus had rings, though they were completely different from Saturn's brilliant ice rings. Uranus's rings were dark as charcoal, made of particles that absorbed almost all the light hitting them. These narrow, rope-like rings were held in place by small shepherd moons that Voyager discovered orbiting between the ring boundaries. The ring particles were probably organic compounds that had been darkened by radiation over millions of years. The planet's moons proved to be just as unusual as Uranus itself. Voyager discovered 10 new moons in addition to the 5 already known from Earth-based observations. These moons were a mixture of ice and rock, but they showed signs of geological activity that seemed impossible for such cold, distant worlds. Some moons displayed evidence of past volcanism or tectonic activity, suggesting that Uranus's gravitational influence could generate enough heat to drive geological processes. The most intriguing moon was Miranda, which looked like it had been smashed apart and reassembled incorrectly. Its surface showed a bizarre patchwork of different terrains, smooth plains next to heavily cratered regions, enormous cliffs taller than the Grand Canyon, and grooved terrain that looked like cosmic corduroy. Miranda appeared to be a geological nightmare, as if several different worlds had been cut up and glued together randomly. 3.5 years after leaving Uranus, Voyager 2 approached the solar system's most distant giant planet. Neptune lurked in the cosmic darkness, receiving only 1/1000th the sunlight that Earth enjoys. Yet, this seemingly frozen world was about to reveal the most dynamic and violent atmosphere in the entire solar system. From a distance, Neptune appeared as a brilliant blue marble, decorated with wispy white clouds that raced across its surface at impossible speeds. Unlike the bland, featureless Uranus, Neptune blazed with atmospheric activity despite receiving so little energy from the distant sun. The planet's deep blue color came from methane in its atmosphere, but Neptune's blue was far more vibrant and intense than Uranus's pale, green-blue tint. Voyager's instruments immediately detected something extraordinary. Winds on Neptune were racing at over 1,500 miles per hour, faster than the speed of sound on Earth. These weren't just gentle breezes. They were supersonic hurricanes that could circle the entire planet in less than 18 hours. The fastest winds in the solar system were blowing on the coldest planet. A paradox that baffled atmospheric scientists. The most prominent feature was a massive storm system that scientists nicknamed the Great Dark Spot, similar to Jupiter's Great Red Spot, but proportionally even larger compared to the planet's size. This cosmic hurricane was big enough to swallow Earth whole, with winds spinning counterclockwise at tremendous speeds around a dark central eye. Unlike Jupiter's ancient storm, Neptune's Great Dark Spot appeared to be a relatively young and dynamic feature. But how could such violent weather exist on a world so far from the sun's warmth? Scientists discovered that Neptune was radiating more than twice as much energy into space as it received from sunlight. The planet was essentially a cosmic furnace, generating its own heat from gravitational compression and leftover energy from its formation 4.5 billion years ago. This internal heat source drove the incredibly active atmosphere, despite the planet's frigid distance from the sun. The white clouds streaking across Neptune's blue surface were made of methane ice crystals that formed high in the atmosphere, where temperatures dropped to -360 degrees Fahrenheit. These clouds moved at different speeds than the underlying atmospheric layers, creating a complex, multi-level weather system with jet streams racing at different altitudes. Some clouds changed dramatically during Voyager's brief encounter, appearing and disappearing within hours. Neptune's magnetic field proved to be just as strange as Uranus's. Tilted 47 degrees from the planet's rotational axis and offset from the center by about half the planet's radius. This similarity to Uranus suggested that extreme magnetic field orientations might be normal for ice giant planets, challenging scientists' understanding of how planetary magnetic fields form and evolve. The planet's largest moon, Triton, immediately caught scientists' attention because it was orbiting backward, the only large moon in the solar system with a retrograde orbit. This suggested that Triton was actually a captured object, probably a dwarf planet similar to Pluto that had been gravitationally captured by Neptune eons ago. The capture process would have been violent, destroying any other large moons that might have originally orbited Neptune. Triton itself proved to be one of the most geologically active worlds in the outer solar system, despite its incredible distance from the sun. Voyager detected nitrogen geysers erupting from Triton's surface, shooting dark material up to 5 miles high into the thin atmosphere. These eruptions were probably driven by solar heating of nitrogen ice beneath Triton's surface, creating pressure that eventually exploded through weak spots in the crust. The discovery of active geology on Triton at such a vast distance from the sun revolutionized scientists' thinking about where geological activity could exist in the solar system. If tiny amounts of solar energy could drive eruptions on Triton, then geological processes might be active throughout the outer solar system, even on worlds that seemed completely frozen and dead. 35 years after launching from Earth, Voyager 1 was racing through space far beyond the orbit of Pluto, carrying instruments that still functioned perfectly despite decades of cosmic radiation and extreme cold. Mission scientists expected the spacecraft to eventually reach a boundary called the heliopause, the edge of our solar system, where the sun's influence finally gives way to interstellar space. But nobody knew exactly where this boundary lay or what it would look like when Voyager found it. The solar system isn't just planets and moons floating in empty space. It's filled with a constant stream of charged particles flowing outward from the sun. Called the solar wind, this invisible river of plasma creates a massive bubble around our entire solar system, pushing against the thin gas that exists between stars. The heliopause marks the boundary where the solar wind finally meets its match and can push no further into the galaxy. As Voyager 1 traveled beyond 100 astronomical units from the Sun, more than 100 times Earth's distance from our star. Its instruments began detecting strange changes in the space environment. The density of cosmic rays from deep space was increasing, while the intensity of particles from the Sun was decreasing. The spacecraft was approaching a cosmic border that had never been crossed by any human-made object. In August 2012, Voyager 1's instruments detected a sudden drop in the number of solar particles reaching the spacecraft, followed by a dramatic increase in cosmic rays from interstellar space. The transition happened within a few days. One moment, Voyager was still inside our solar system. The next, it had crossed into the space between stars. After 35 years of travel, humanity had finally touched the edge of home. The heliopause wasn't a sharp wall, as scientists had expected. It was more like a boundary layer where solar and interstellar influences gradually blended together. The magnetic field strength remained relatively constant across the boundary, suggesting that interstellar space was more organized and structured than anyone had predicted. Instead of crossing into cosmic chaos, Voyager found that the space between stars had its own magnetic highways and particle flows. But the most surprising discovery was how different interstellar space felt compared to the solar environment Voyager had known all its life. The background noise of plasma waves changed dramatically, like stepping from a busy highway into a quiet forest. The cosmic ray environment was more intense, but also more steady, without the fluctuations caused by solar storms and magnetic field changes from our Sun. Scientists realized they were receiving the first direct measurements of the local interstellar medium, the thin soup of gas and dust that fills the space between stars in our galaxy. This material was the leftover debris from ancient supernovae and stellar winds, seasoned with heavy elements forged in the nuclear furnaces of long-dead stars. Voyager was sampling the very substance from which new stars and planets would eventually form. The crossing also revealed that our solar system was moving through interstellar space at about 52,000 miles per hour, relative to the nearby stars. This motion created a bow shock ahead of our solar system, like the wake of a boat moving through water. Voyager's measurements helped scientists map this cosmic bow wave and understand how our solar system interacted with the galactic environment around it. Temperature measurements showed that interstellar space was actually warmer than the outer regions of our solar system, heated by cosmic rays and starlight from the Milky Way galaxy. The interstellar medium had a temperature of about 80,000 degrees Fahrenheit, though the gas was so thin that a thermometer would read near absolute zero due to the lack of particles to transfer heat. As Voyager 1 continued deeper into interstellar space, it was writing the first chapter of humanity's exploration beyond our solar system, carrying its golden record message into the cosmic ocean between stars. 6 years after Voyager 1 crossed the heliopause, its twin spacecraft was approaching the same historic boundary from a different direction. Voyager 2 had taken a different path through the outer solar system, using gravitational assists to visit all 4 giant planets before heading toward its own rendezvous with interstellar space. When it finally crossed the boundary in November 2018, the data it sent back revealed that the edge of our solar system was far more complex than anyone had imagined. Unlike Voyager 1's relatively smooth transition, Voyager 2 experienced a much more turbulent crossing. The spacecraft detected multiple boundary crossings over several months, as if the heliopause was rippling like a flag in a cosmic wind. Sometimes Voyager 2 was in interstellar space. Other times, it was back in the solar wind, and occasionally, it seemed to be in a strange middle ground where neither environment dominated. The 2 spacecraft revealed that the heliosphere, our solar system's protective bubble, wasn't a perfect sphere at all. It was lopsided and constantly changing shape as it plowed through the interstellar medium. The sun's magnetic field and solar wind created a complex, three-dimensional structure that varied depending on solar activity and the changing galactic environment our solar system encountered. Voyager 2's working plasma instrument provided the first direct measurements of interstellar plasma density and temperature. The data showed that interstellar space was filled with a thin but measurable gas that was significantly denser than the solar wind that had surrounded both spacecraft for decades. This interstellar material was being compressed and heated by our solar system's passage through it, creating a bow shockwave ahead of our cosmic motion. Both Voyagers detected something unexpected. The magnetic field in local interstellar space was much stronger and more organized than theoretical models had predicted. Instead of the weak, chaotic magnetic environment scientists expected, the spacecraft found well-defined magnetic highways that channeled cosmic rays and charged particles across vast distances. These magnetic field lines were probably connected to nearby star-forming regions and supernova remnants. The cosmic ray environment in interstellar space proved to be dramatically different from anything measured inside our solar system. High-energy particles from distant galactic sources bombarded both spacecraft constantly, creating a radiation environment that would be lethal to unprotected humans. These cosmic rays carried information about stellar explosions, neutron stars, and black holes throughout our local region of the galaxy. Temperature measurements revealed the strange physics of interstellar space. While the plasma temperature was tens of thousands of degrees, the actual gas density was so low that a human would instantly freeze to death. The few atoms present were moving at incredible speeds due to their high temperature. But there were so few of them that they couldn't transfer meaningful amounts of heat to solid objects. Scientists realized that both Voyagers were now sampling the raw material from which stars and planets form throughout the galaxy. The interstellar medium contained hydrogen and helium left over from the Big Bang, mixed with heavier elements forged in stellar cores and dispersed by supernova explosions. This cosmic recycling process had been enriching the galaxy with heavy elements for billions of years. The data streaming back from both spacecraft was rewriting textbooks about the structure of our solar system and its place in the galaxy. The heliosphere wasn't just a static bubble. It was a dynamic structure that breathed and flexed as our solar system encountered different regions of interstellar space during its orbit around the galactic center. As Voyager 1 approached Jupiter, mission controllers knew they were sending their precious spacecraft into one of the most dangerous environments in the solar system. Jupiter's immense magnetic field, 20,000 times stronger than Earth's, trapped high-energy particles in invisible belts that surrounded the planet like cosmic death rays. These radiation belts could fry electronic circuits in minutes and would kill any unprotected human almost instantly. The radiation environment around Jupiter was so intense that it made the Van Allen belts surrounding Earth look like a gentle summer rain compared to a Category 5 hurricane. Charged particles spiraled back and forth along Jupiter's magnetic field lines at nearly the speed of light, creating a particle accelerator that dwarfed anything humans had built on Earth. The radiation was intense enough to damage Voyager's cameras and instruments, even through their protective shielding. Scientists discovered that Jupiter's radiation belts were fed by material from Io's volcanic eruptions. The sulfur and oxygen blasted into space by Io's volcanoes became ionized by Jupiter's radiation, creating a donut-shaped cloud of charged particles that orbited the planet. These particles were then accelerated to incredible energies by Jupiter's rotating magnetic field, turning peaceful volcanic gases into cosmic bullets moving at relativistic speeds. The radiation environment varied dramatically depending on distance from Jupiter and position relative to the planet's magnetic field. Near Io's orbit, the radiation was so intense that it would deliver a lethal dose to a human in less than 1 second. even at Europa's distance. The radiation levels were thousands of times higher than anything experienced on Earth, enough to kill in minutes, despite being much farther from Jupiter's surface. Voyager's instruments detected radio emissions from Jupiter's radiation belts that could be heard on Earth with simple shortwave radios. These emissions were created when high-energy electrons spiraled through Jupiter's magnetic field, generating radio waves that propagated across the solar system. Amateur radio operators had been detecting these Jovian radio bursts for decades without understanding their origin. The spacecraft's passage through Jupiter's radiation environment provided the first direct measurements of how planetary magnetic fields trap and accelerate charged particles. Scientists realized they were studying a natural particle accelerator that had been operating for billions of years, creating conditions more extreme than anything that could be reproduced in terrestrial laboratories. Temperature measurements showed that Jupiter's radiation belts were incredibly hot. Not in the traditional sense, but in terms of particle energy. Individual electrons and protons in the belts had temperatures equivalent to millions of degrees, though the low particle density meant that solid objects wouldn't be heated by conduction. Instead, the danger came from radiation damage as high-energy particles smashed through electronic components. The radiation belts also affected Jupiter's moons in different ways. Io, orbiting deep within the most intense radiation, had its atmosphere constantly stripped away and replenished by volcanic activity. Europa's ice surface was bombarded by radiation that broke water molecules apart, creating a thin oxygen atmosphere through radiolysis. Ganymede's magnetic field provided some protection, while Callisto orbited far enough out to avoid the worst radiation. When Voyager 1 glimpsed Saturn's North Pole in 1980, mission scientists thought they were seeing an optical illusion or a camera malfunction. The images showed what appeared to be a perfectly geometric hexagon surrounding Saturn's northern polar region, a six-sided storm system that looked more like artificial architecture than natural weather. No planet had ever been observed with geometric weather patterns, and the discovery challenged everything meteorologists thought they knew about atmospheric dynamics. The hexagon was enormous, spanning nearly 15,000 miles from side to side, wide enough to fit 2 Earths inside with room to spare. Each side of this cosmic geometry was longer than the diameter of Earth, making it one of the largest coherent structures ever observed in any planetary atmosphere. The hexagon appeared to be a jet stream of sorts, with winds racing around its perimeter at over 200 miles per hour in a perfectly straight-sided pattern. But how could nature create such a geometrically perfect structure? Storms on Earth and other planets typically form circular or oval patterns because rotating fluids naturally organize into curved flows. The idea of a hexagonal hurricane seemed to violate the basic laws of fluid dynamics. Yet there it was, spinning majestically around Saturn's North Pole like a cosmic snowflake drawn by an impossibly precise hand. Scientists realized they were witnessing something that had probably been stable for decades or even centuries. The hexagon wasn't a temporary weather pattern. It was a permanent feature of Saturn's atmosphere, as persistent as the great red spot on Jupiter, but far more geometrically precise. The structure showed no signs of breaking up or changing shape, maintaining its perfect six-sided form despite the chaotic turbulence of the surrounding atmosphere. Laboratory experiments later revealed how such geometric patterns could form in rotating fluids. When a circular jet stream is disturbed by specific types of waves, it can lock into polygon shapes with 3, 4, 5, 6, or even more sides, depending on the wave characteristics. Saturn's hexagon represented a natural example of this phenomenon, scaled up to planetary proportions, creating geometric perfection through the complex mathematics of fluid dynamics. The center of the hexagon contained a massive hurricane with a clearly defined eye. similar to terrestrial hurricanes, but much larger and more persistent. This central storm was about the size of Earth and appeared to be the anchor point around which the hexagonal jet stream organized itself. Winds in the eye wall reached speeds of over 300 miles per hour, making it one of the most intense storms in the solar system. Temperature measurements showed that the hexagon was actually a cold feature compared to the surrounding atmosphere. The geometric jet stream acted like a barrier, preventing warm air from the equatorial regions from mixing with the polar atmosphere. This temperature difference helped maintain the sharp boundaries that gave the hexagon its precise edges, creating a self-reinforcing system that could persist for geological time periods. The discovery of Saturn's hexagon proved that planetary atmospheres could create structures of stunning mathematical beauty and precision. The storm represented a perfect marriage of chaos and order, where the random turbulence of atmospheric convection organized itself into one of the most geometrically perfect natural structures ever observed in the solar system. When Voyager 2 flew past Uranus in 1986, scientists expected to find a magnetic field similar to Earth's, roughly aligned with the planet's rotation axis and centered on the planetary core. Instead, they discovered one of the most bizarre and twisted magnetic environments in the entire solar system. A cosmic compass that seemed to have been shattered and reassembled incorrectly by some ancient catastrophe. Uranus's magnetic field was tilted 59 degrees away from the planet's rotation axis, as if someone had grabbed a bar magnet and twisted it nearly sideways before shoving it back inside the planet. Even more strangely, the magnetic field didn't even pass through Uranus's center. It was offset by about 1/3 of the planet's radius, creating a lopsided magnetic environment unlike anything found around any other planet. The magnetic field strength varied wildly depending on location around Uranus. In some regions, it was stronger than Earth's magnetic field, while in other areas, it was barely detectable. This created a chaotic magnetosphere where charged particles followed twisted, unpredictable paths instead of the organized radiation belts found around other planets. Voyager's instruments detected particles spiraling in corkscrew patterns that defied conventional models of planetary magnetism. Scientists struggled to explain how such a distorted magnetic field could exist. On Earth, the magnetic field is generated by electric currents in the molten iron core, creating a relatively stable dipole field that resembles a giant bar magnet. But Uranus's magnetic field seemed to originate from multiple sources scattered throughout the planet's interior, as if several smaller magnetic generators were operating independently inside the world. The discovery suggested that Uranus had suffered some kind of catastrophic event in its past that completely scrambled its internal structure. The same collision that knocked the planet onto its side might have disrupted the normal convection patterns in its interior, creating the chaotic magnetic field configuration that Voyager observed. This cosmic accident had left Uranus with a magnetic environment that was fundamentally different from every other planet. The twisted magnetic field created equally twisted auroras around Uranus's poles, instead of the elegant curtains of light that dance around Earth's polar regions. Uranus's auroras appeared as chaotic knots and spirals that moved unpredictably across the planet's atmosphere. These alien light shows were powered by the same charged particles that create Earth's auroras, but the distorted magnetic field channeled them in completely different patterns. Temperature measurements revealed that Uranus's magnetosphere was surprisingly cold compared to other planets. The chaotic magnetic field couldn't efficiently trap and heat charged particles like the organized magnetic environments around Jupiter and Saturn. This created a magnetosphere that was not only twisted, but also relatively inactive compared to the dynamic particle environments around other giant planets. The magnetic field measurements also revealed something unexpected about Uranus's interior structure. The planet appeared to have distinct layers with different electrical properties, suggesting that Uranus was more like a partially mixed cocktail than the well-stirred fluid interiors found in Jupiter and Saturn. Water, methane, and ammonia ices might exist in separate layers deep inside the planet, each contributing differently to the overall magnetic field. Voyager's magnetometer continued detecting strange magnetic signatures even as the spacecraft departed Uranus. The planet's magnetic tail, the region where the magnetic field stretches away from the sun, was twisted into a helical pattern that rotated like a cosmic corkscrew as Uranus spun on its tilted axis. This created a magnetic signature unlike anything else in the solar system. The bizarre magnetic environment around Uranus demonstrated that planetary magnetic fields could be far more complex and chaotic than scientists had previously imagined, providing clues about the violent processes that shape the outer planets during the solar system's formation. When Voyager 2 captured images of Neptune's Great Dark Spot in 1989, scientists assumed they were documenting a permanent feature similar to Jupiter's ancient Great Red Spot. This massive storm system was proportionally larger than Jupiter's famous hurricane, big enough to contain the entire Earth within its swirling winds. But when the Hubble Space Telescope turned its gaze toward Neptune just 5 years later, the Great Dark Spot had completely vanished without a trace. The disappearance of such a massive storm system baffled atmospheric scientists. On Jupiter, the Great Red Spot had been raging for at least 3 centuries and showed no signs of weakening. How could Neptune's equally impressive storm simply evaporate in less than a decade? The answer revealed fundamental differences between the atmospheric dynamics of gas giant planets and ice giants like Neptune. Neptune's atmosphere was far more dynamic and turbulent than Jupiter's, driven by the planet's internal heat source rather than solar energy. The rapid atmospheric changes meant that storm systems could form and dissipate much more quickly than on Jupiter, where the thicker atmosphere and lower energy density created more stable weather patterns. Neptune was essentially a cosmic weather laboratory, where atmospheric features appeared and disappeared on human timescales. The Great Dark Spot wasn't just any storm, it was an anticyclonic system, with winds rotating in the opposite direction from the planet's rotation. These high-pressure systems are relatively rare in planetary atmospheres and require specific conditions to form and maintain themselves. When those conditions changed, the storm couldn't sustain itself and gradually dissolved into the surrounding atmospheric chaos. Hubble's continued observations revealed that Neptune regularly produces and destroys large dark spots in its atmosphere. New storm systems would appear in different locations, grow to enormous sizes, persist for months or years, then fade away as atmospheric conditions shifted. Neptune's atmosphere was like a cosmic storm factory, constantly creating and recycling massive weather systems. The vanishing act of the Great Dark Spot demonstrated that Neptune's atmosphere was far more active than its distance from the sun would suggest. Despite receiving only 1/1000th the solar energy that Earth enjoys, Neptune generated the most dynamic weather in the solar system through its powerful internal heat source. The planet was radiating 2.5 times more energy than it received from the sun, creating atmospheric instability that drove rapid weather changes. Scientists realized that the ice giant planets, Uranus and Neptune, operated by completely different rules than the gas giants Jupiter and Saturn. While Jupiter and Saturn had relatively stable atmospheric features that persisted for centuries, the ice giants showed rapid atmospheric evolution that could completely reshape their appearance within decades. This made them much more challenging to study and understand. The discovery that major atmospheric features could appear and disappear so quickly revolutionized how scientists thought about planetary weather systems. It suggested that many planets might have highly variable atmospheres where dramatic changes occur on human timescales rather than geological time periods. This variability made the ice giants some of the most dynamic worlds in the solar system. Temperature and wind measurements showed that Neptune's atmospheric activity was driven by powerful convection currents that transported heat from the planet's interior to its upper atmosphere. These convection cells created and destroyed weather systems as they organized and reorganized themselves. Like cosmic thunderstorms that could spawn hurricane-sized vortices. The rapid atmospheric evolution also suggested that Neptune's weather might be influenced by seasonal changes as the planet orbited the Sun. With each season lasting over 40 Earth years, atmospheric patterns might shift on decadal timescales as different hemispheres experience changes in solar heating. Attached to each Voyager spacecraft was perhaps the most ambitious message ever created. A golden phonograph record containing sounds, images, and greetings from Earth, designed to communicate with any alien civilization that might find the spacecraft in the distant future. This cosmic time capsule represented humanity's first attempt to introduce ourselves to intelligence beyond our solar system. The golden record contained 115 images depicting life on Earth, from scientific diagrams showing human anatomy and DNA structure to photographs of people from different cultures around the world. The record included sounds of Earth, everything from whale songs and bird calls to a crying baby and the footsteps of someone walking. Musical selections ranged from Bach and Beethoven to traditional folk songs from different cultures, creating a sonic portrait of human civilization. Creating this interstellar message required solving unprecedented communication challenges. How do you explain human concepts to minds that might think in completely alien ways? The record began with basic mathematical and physical concepts that any technological civilization would understand, using these universal principles as a foundation for more complex information about Earth and humanity. The cover of the golden record contained instructions for playing it, engraved as diagrams that showed how to construct a stylus and determine the correct playing speed. These instructions use the spin transition of hydrogen atoms as a universal time reference, since any civilization advanced enough to intercept Voyager would understand atomic physics. The diagrams also showed the position of our Sun relative to 14 nearby pulsars, creating a cosmic address that aliens could use to locate Earth. Spoken greetings in 55 human languages were included on the record, from ancient Sumerian to modern Mandarin Chinese. Each greeting was a simple message of peace and goodwill, acknowledging that any beings capable of finding and playing the record would possess technology far beyond our own. The variety of languages demonstrated the diversity of human culture while emphasizing our common desire for communication and understanding. The record also contained an hour and a half of music that told the story of human creativity and emotion. Classical compositions demonstrated our mathematical understanding of harmony and rhythm, while folk songs revealed the cultural diversity that flourished across our planet. The musical selections were chosen to represent the full range of human expression, from joy and celebration to melancholy and spiritual reflection. Scientific information on the record included diagrams of human reproduction, the structure of DNA, and mathematical definitions of basic physical constants. These images attempted to explain what humans are as biological entities and how we understand the universe around us. The record even included a diagram showing the trajectory of the Voyager spacecraft themselves, indicating where they came from in our solar system. But perhaps the most poignant aspect of the golden record was its representation of Earth as our home. Images showed our planet from space, revealing the blue marble hanging in the cosmic darkness that represents the only known haven for life in the universe. Other images depicted Earth's environments, oceans, forests, deserts, and cities, showing the incredible diversity of landscapes that exist on our world. The golden record was designed to last for billions of years in the vacuum of space, outliving human civilization and possibly even our sun. The gold-plated copper disc was protected by an aluminum cover that would shield it from cosmic radiation and micrometeorite impacts during its journey through interstellar space. If aliens ever found it, they would be discovering a message from a species that might no longer exist. Among Jupiter's 4 largest moons, Ganymede stood out as an anomaly from the moment Voyager 1 detected its unusual properties. This ice-covered world, larger than the planet Mercury, possessed something that no other moon in the solar system could claim: its own internally generated magnetic field. Strong enough to carve out a protective magnetosphere within Jupiter's deadly radiation environment. Ganymede's magnetic field was a complete surprise to planetary scientists. Moons weren't supposed to generate their own magnetic fields. They were too small and cool to maintain the molten, convecting cores that power planetary magnetism. Yet Voyager's instruments clearly detected magnetic signatures indicating that Ganymede was somehow generating its own magnetic bubble, creating a safe harbor within Jupiter's particle storm. The discovery revolutionized our understanding of how magnetic fields form and persist in small planetary bodies. Ganymede's magnetic field suggested that the moon had a partially molten iron core, similar to Earth's, but on a much smaller scale. Tidal heating from Jupiter's gravity was apparently generating enough energy to keep part of Ganymede's core liquid, allowing electric currents to flow and create magnetic fields through dynamo action. This magnetic shield had profound implications for Ganymede's habitability potential. While Europa and Io were constantly bombarded by Jupiter's intense radiation, Ganymede's magnetosphere deflected most of the high-energy particles away from its surface. The magnetic field created a relatively protected environment where complex chemistry could occur without being immediately destroyed by radiation. Temperature and particle measurements revealed that Ganymede's magnetosphere was surprisingly effective at excluding Jovian radiation. The magnetic field strength was only about 1% of Earth's, but it was strong enough to create distinct regions where solar wind particles from Jupiter were excluded or redirected. This created a miniature version of Earth's protective magnetic environment around a moon that was only slightly larger than Mercury. The magnetic field also suggested that Ganymede had a much more complex internal structure than previously thought. Instead of being a simple ball of ice and rock, the moon appeared to have differentiated into distinct layers: an iron core, a rocky mantle, and multiple ice layers, similar to the internal structure of terrestrial planets. This level of differentiation required significant heating and geological activity early in Ganymede's history. Voyager's magnetometer detected variations in Ganymede's magnetic field that indicated the field was not perfectly stable. The magnetic poles appeared to wander slightly, and the field strength varied depending on Ganymede's position in its orbit around Jupiter. These variations suggested that the moon's magnetic dynamo was influenced by tidal forces from Jupiter, creating a complex interaction between orbital mechanics and internal geology. The presence of a magnetic field also affected Ganymede's thin atmosphere in unexpected ways. Charged particles trapped in the moon's magnetosphere created auroras at Ganymede's poles, similar to the northern and southern lights on Earth, but much fainter due to the thin atmosphere. These alien auroras were visible only in ultraviolet light and represented the first auroras ever detected around a moon. Scientists realized that magnetic fields might be more common among large moons than previously thought. If Ganymede could generate its own magnetic field, other large moons throughout the solar system might possess similar capabilities. This opened up new possibilities for finding magnetically protected environments where life might persist despite harsh radiation conditions around giant planets. The discovery of Ganymede's magnetic field demonstrated that small worlds could be far more geologically active and complex than their size would suggest. It showed that the traditional view of moons as simple, inactive bodies was fundamentally wrong. They could be dynamic worlds with their own protective systems and complex internal processes. When Voyager 2 flew past Uranus's small moon, Miranda, in January 1986, it revealed one of the most bizarre and chaotic landscapes ever discovered in the solar system. This tiny world, only 300 miles across, looked like it had been smashed to pieces and then carelessly reassembled by cosmic forces beyond imagination. The surface showed a nightmarish patchwork of different terrains that seemed to defy every principle of planetary geology. Miranda's surface was divided into distinct regions that looked like they belonged on completely different worlds. Smooth, relatively young plains sat next to ancient, heavily cratered terrain, enormous. Grooved regions called coronae showed parallel ridges and valleys that stretched for hundreds of miles, while massive cliffs towered over landscapes that appeared to have been turned inside out. The moon looked like a cosmic jigsaw puzzle where none of the pieces quite fit together. The most spectacular feature was Uranus, a cliff that plunged 12 miles straight down, the tallest known cliff face in the entire solar system. To put this in perspective, if you could somehow fall off this cliff, it would take you over 10 minutes to hit the bottom due to Miranda's weak gravity. The cliff was so tall that a person jumping from the top would have time to take a short nap before reaching the bottom. Scientists struggled to explain how such diverse terrain could exist on such a small world. Miranda was too tiny to have retained significant internal heat from its formation. Yet the surface showed clear evidence of recent geological activity. The grooved terrain looked like it had been stretched and twisted by powerful forces, while the smooth plain suggested that some kind of resurfacing process had erased older features. One theory suggested that Miranda had been literally shattered by a massive impact sometime in the distant past, breaking the moon into multiple pieces that later reassembled under their own gravity. This catastrophic breakup and reformation could explain the chaotic mixture of terrain types. Different pieces of the original moon had been jumbled together when gravity pulled the fragments back into a spherical shape. But tidal heating from Uranus provided a more plausible explanation for Miranda's geological chaos. Despite its small size, Miranda orbited relatively close to Uranus and was locked in orbital resonances with other moons that amplified tidal forces. These gravitational effects could have generated enough heat to drive geological activity, creating the grooved terrain and smooth plains through a process similar to what powers volcanoes on Io. The grooved regions showed evidence of extensional tectonics, where the surface had been stretched and pulled apart to create parallel ridges and valleys. This type of terrain indicated that Miranda's crust had been under tension, possibly due to tidal bulges created by Uranus's gravity. The moon was essentially being kneaded like cosmic bread dough, causing its surface to crack and reshape itself over geological time. Temperature measurements revealed that Miranda was one of the coldest worlds ever visited by a spacecraft, with surface temperatures around -300 degrees Fahrenheit. At these frigid temperatures, water ice behaved like solid rock, allowing it to form the massive cliffs and grooved terrain that dominated the landscape. The extreme cold also meant that any geological processes had to be driven by internal heat sources rather than solar warming. The diverse terrain types suggested that Miranda had experienced multiple episodes of geological activity separated by long periods of dormancy. Different regions of the moon appear to have been active at different times, creating the patchwork appearance that made Miranda look like a geological museum displaying samples from throughout its history. As Voyager 1 approached Saturn's magnificent ring system, scientists expected to find a relatively simple structure, bands of particles orbiting the planet in neat, orderly rings separated by empty gaps. Instead, they discovered one of the most complex and dynamic systems in the solar system, where tiny moons acted like cosmic shepherds, controlling the behavior of trillions of ring particles through their gravitational influence. The most dramatic example was discovered in Saturn's narrow F ring, where two small moons named Prometheus and Pandora orbited on either side of the ring, like cosmic border collies herding a flock of ice particles. These shepherd moons used their gravity to confine the ring particles to a narrow band, preventing them from spreading out or drifting away from Saturn. Without these gravitational shepherds, the F ring would have dispersed into space long ago. Prometheus and Pandora created a gravitational dance that kept the F ring particles in line through a complex process of orbital resonances. When ring particles drifted too close to the inner shepherd moon, Prometheus, they were gravitationally accelerated, which raised their orbits and pushed them back toward the center of the ring. Particles that wandered too far outward encountered Pandora, which slowed them down and lowered their orbits back into the ring. But this gravitational herding wasn't a gentle process. Voyager's images revealed that the F ring was constantly being disturbed by the shepherd moons, creating kinks, braids, and clumps that changed dramatically over just a few hours. The ring looked like cosmic spaghetti being twisted and braided by invisible hands, with some sections appearing to be woven together like rope, while others showed dramatic kinks and knots. The shepherd moons weren't the only gravitational sculptors at work in Saturn's rings. Voyager discovered that many of the gaps between ring sections were maintained by small moons embedded within the ring system itself. These embedded moonlets swept up ring particles in their immediate vicinity, creating gaps and maintaining sharp edges between different ring sections through gravitational clearing. One of the most spectacular examples was the Encke Gap, a narrow division in Saturn's A-ring that was maintained by a small moon called Hun. This tiny shepherd, only about 20 miles across, orbited within the gap and used its gravity to keep the gap clear of ring particles. Pan's gravitational influence created spiral density waves that propagated through the surrounding ring material like cosmic ripples. The ring particles themselves weren't passive victims of gravitational herding. They actively responded to the shepherd moons through complex resonance effects. When ring particles completed exact fractions of an orbit for every orbit of a shepherd moon, they experienced regular gravitational tugs that could either confine them to specific regions or eject them from the ring system entirely. These resonances created intricate patterns throughout Saturn's rings. Scientists realized they were watching a cosmic ballet where gravity choreographed the movements of countless particles through the influence of small moons. The shepherd moons and ring particles were locked in gravitational relationships that had been stable for millions of years, creating one of the most precisely organized structures in the solar system. Each particle knew its place in this cosmic dance, guided by invisible gravitational forces. Temperature measurements revealed that the shepherd moons were influencing more than just particle orbits. They were also affecting the thermal properties of the rings. Areas near shepherd moons showed different temperatures than the surrounding ring material, suggesting that gravitational interactions were generating heat through particle collisions and tidal friction. The discovery of shepherd moons revolutionized our understanding of how ring systems form and evolve around planets throughout the universe. Scientists realized that planetary rings weren't static structures, but dynamic systems constantly shaped by gravitational interactions with nearby moons. The shepherd moons proved that even tiny objects could exert enormous influence over vast regions of space through the precise application of gravitational force. as both Voyager spacecraft traveled through the solar system and beyond. Their instruments detected something that challenged the popular notion that space is completely silent. Hidden within the vacuum of space, electromagnetic waves were singing songs that no human ear could hear. Plasma waves that created a cosmic symphony of radio emissions spanning the entire electromagnetic spectrum. These weren't sound waves that could travel through air like music on Earth. Instead, they were electromagnetic oscillations in the thin plasma that fills the space between planets, creating radio frequencies that Voyager's instruments could detect and convert into audio signals. When scientists played back these recordings, they heard the eerie voices of planets, moons, and magnetic fields calling out across the cosmic darkness. Jupiter's magnetosphere produced some of the most dramatic plasma wave emissions, generating radio signals so powerful they could be detected by simple shortwave radios on Earth. As Voyager passed through Jupiter's magnetic field, the spacecraft recorded whistling sounds created by lightning in the planet's atmosphere, along with strange chorus effects generated by electrons spiraling through the magnetic field lines. Jupiter was broadcasting its own radio station across the solar system. Saturn's plasma waves told a different story. They revealed the complex interactions between the planet's rings and its magnetosphere. As charged particles from Saturn's magnetic field collided with ring particles, they created electromagnetic disturbances that propagated through space like cosmic thunder. Voyager detected these collisions as crackling static, punctuated by mysterious musical tones that seemed to come from the rings themselves. The most haunting sounds came from the space between planets, where the solar wind created its own electromagnetic symphony. As the stream of charged particles from the Sun encountered magnetic obstacles like planetary magnetospheres or interplanetary magnetic field boundaries, it generated bow shock waves that produced distinctive whistling and whooshing sounds. These were the sounds of the solar wind itself, singing as it flowed past obstacles in its path. Voyager's plasma wave instrument could detect frequencies ranging from 10 Hz to 56 kHz, covering the range of human hearing when converted to audio. Scientists discovered that different types of plasma waves had characteristic signatures. Electron-cyclotron waves sounded like bird songs, while ion acoustic waves resembled ocean surf. Each region of space had its own acoustic fingerprint, created by the local plasma environment. The most significant plasma wave discovery came when Voyager 1 crossed the heliopause and entered interstellar space. The spacecraft detected a dramatic change in the background plasma wave environment, like stepping from a noisy room into a quiet library. The chaotic radio emissions from solar wind turbulence were replaced by the more organized plasma waves of the interstellar medium, marking humanity's first direct detection of sounds from beyond our solar system. Scientists realized that plasma waves weren't just acoustic curiosities. They were powerful diagnostic tools for understanding space environments. The frequency, amplitude, and propagation characteristics of these waves revealed information about plasma density, temperature, and magnetic field strength that couldn't be obtained any other way. Voyager was essentially using space as a giant musical instrument to probe the physics of planetary magnetospheres. The plasma wave emissions also revealed dynamic processes that were invisible to optical cameras. Voyager detected plasma waves generated by particle precipitation into planetary atmospheres, creating the electromagnetic signatures of auroras on worlds too far away to photograph directly. The spacecraft could hear auroras on planets where it couldn't see them, extending its sensory capabilities beyond the limitations of visible light. Some of the most mysterious plasma waves came from interactions between planetary moons and their parent planets' magnetic fields. As moons like Io and Europa moved through Jupiter's magnetosphere, They generated electrical currents that produced distinctive radio emissions. These electromagnetic interactions created a form of magnetic coupling between moons and planets that was previously unknown. Throughout their 45-year journey, both Voyager spacecraft served as cosmic surveyors, mapping invisible boundaries created by the solar wind as it flowed outward from the sun and encountered various obstacles in its path. These boundary regions weren't marked by visible features. They were defined by sudden changes in magnetic fields, particle densities, and plasma wave activity that revealed the hidden architecture of our solar system. The first major boundary each Voyager encountered was the bow shock ahead of Jupiter's magnetosphere. Here, the solar wind, traveling at over 1 million miles per hour, slammed into Jupiter's magnetic field and was forced to slow down and change direction. This created a standing shock wave in space, similar to the sonic boom created by a supersonic aircraft, but formed by charged particles instead of sound waves. At each giant planet, Voyager discovered that the solar wind carved out distinct regions with their own characteristic properties. The magnetosheath, the turbulent region between the bow shock and the magnetosphere, was filled with heated and compressed solar wind particles that had been processed by their passage through the shock. Inside each planet's magnetosphere, the solar wind was completely excluded, creating protected cavities where planetary magnetic fields dominated. These boundary regions weren't static walls. They breathed and flexed as solar wind conditions changed. When the sun released particularly strong bursts of particles during solar storms, planetary magnetospheres compressed like cosmic balloons being squeezed. During quiet periods, they expanded outward, pushing their boundaries farther into space. Voyager witnessed these dynamic changes in real time as magnetic field readings fluctuated wildly. Saturn's magnetosphere proved to be particularly responsive to solar wind variations because its magnetic field was weaker than Jupiter's. Voyager detected occasions when Saturn's magnetosphere was so compressed by strong solar wind pressure that some of the planet's moons were temporarily exposed to direct solar wind bombardment. The boundary between Saturn's protected magnetosphere and interplanetary space could shift by hundreds of thousands of miles within hours. But the most significant boundary discovery came when Voyager 1 detected the termination shock in December 2004, the region where the solar wind itself finally encountered enough resistance from interstellar space to slow down from supersonic to subsonic speeds. This boundary marked the beginning of the heliopause, a turbulent region where solar wind particles were slowed, heated, and compressed as they prepared for their final confrontation with interstellar space. The termination shock wasn't a simple, well-defined boundary like planetary bow shocks. Instead, it was a complex, multi-layered region where the solar wind underwent a gradual transition from high-speed flow to slow, turbulent motion. Voyager 1 crossed this boundary multiple times as shock waves and instabilities caused it to move back and forth across the spacecraft's trajectory, creating a cosmic ping-pong effect. Temperature measurements revealed that crossing these boundaries involved dramatic changes in particle energy. Solar wind particles were heated to millions of degrees as they passed through shock waves, while magnetic field compressions created regions where particle densities increased by factors of 10 or more. These boundary regions were cosmic particle accelerators, where gentle solar wind was transformed into high-energy plasma. The boundaries also acted as cosmic filters, allowing some types of particles to pass while blocking others. Planetary magnetospheres excluded most solar wind particles, but allowed cosmic rays from deep space to penetrate. The heliosphere excluded most interstellar particles, but allowed the solar wind to flow freely outward. Each boundary represented a different balance between competing forces in the cosmic environment. Scientists realized that similar boundary regions probably existed around every star in the galaxy. creating a complex network of invisible structures that channeled the flow of charged particles through interstellar space. Understanding these solar system boundaries provided insights into how stellar winds interact throughout the Milky Way galaxy, revealing fundamental processes that shape the cosmic environment around all stars. When both Voyager spacecraft began their grand tour of the outer planets, scientists thought they understood how planetary magnetic fields worked. Earth's magnetic field provided the template, a relatively simple dipole field, aligned with the planet's rotation axis and generated by electric currents in the molten iron core. But Voyager's magnetic field measurements from Jupiter, Saturn, Uranus, and Neptune shattered these assumptions and forced a complete rewrite of planetary magnetism theories. Jupiter's magnetic field was the first shock. Instead of being roughly aligned with the planet's rotation like Earth's field, Jupiter's magnetic axis was tilted 11 degrees off-center and was significantly more complex than any theoretical models had predicted. The field strength was 20,000 times more powerful than Earth's, creating a magnetosphere so large it could easily contain the Sun. If visible to the naked eye, Jupiter's magnetosphere would appear larger than the full moon when viewed from Earth. But Jupiter's magnetic complexity was nothing compared to the revelations that awaited at Uranus and Neptune. Both ice giant planets had magnetic fields tilted at impossible angles, 59 degrees for Uranus and 47 degrees for Neptune. These weren't minor measurement errors. They represented fundamental differences in how magnetic fields could be generated inside planets. The traditional model of magnetic fields originating in planetary cores clearly didn't apply to these worlds. Even more puzzling was the discovery that both Uranus and Neptune had magnetic fields that didn't even pass through their centers. The magnetic dipoles were offset by significant fractions of each planet's radius, as if invisible bar magnets had been shoved partway inside each world and left floating off-center. This configuration violated every principle scientists thought they understood about planetary magnetism. Saturn provided yet another magnetic mystery. Its magnetic field was almost perfectly aligned with the planet's rotation axis, so perfectly aligned that it seemed physically impossible. Theoretical models suggested that no planetary magnetic field could be that precisely organized without some external mechanism maintaining the alignment. Saturn's magnetic field was too perfect to be natural, yet it clearly existed. The magnetic field measurements also revealed dynamic processes that had never been observed before. Jupiter's magnetic field was constantly fluctuating as the planet's rapid rotation dragged charged particles around in complex patterns. The magnetosphere rotated with the planet every 10 hours, creating a cosmic magnetic lighthouse that swept charged particle beams across space like rotating searchlights. Voyager discovered that planetary magnetic fields weren't isolated phenomena. They were intimately connected to their host planets, moons, and ring systems. Io's volcanic eruptions fed material into Jupiter's magnetosphere, creating a donut-shaped cloud of charged particles that modified the entire magnetic environment. Saturn's rings interacted with the planet's magnetic field to create spokes and other mysterious features that couldn't be explained by gravitational forces alone. The spacecraft also revealed that magnetic fields could be generated in unexpected places. Ganymede's small magnetic field proved that moons could create their own magnetospheres within their parent planet's magnetic environments. Even some asteroids and comets showed evidence of weak magnetic fields, suggesting that magnetism was far more common in the solar system than previously thought. Temperature and particle measurements showed that planetary magnetic fields were powerful shapers of space environments. They trapped charged particles in radiation belts, accelerated particles to incredible energies, and created complex electrical circuits that linked planets to their moons through invisible magnetic field lines. Magnetic fields weren't just passive phenomena. They were active players in planetary system dynamics. The magnetic field discoveries forced scientists to develop entirely new theories about how planetary magnetism works. Instead of simple dipole fields generated in cores, planets appeared to have complex magnetic dynamos operating at different depths and with different orientations. The magnetic field generation process was clearly much more complicated than anyone had imagined. These revelations about planetary magnetism had implications far beyond our solar system. If the magnetic fields around the planets in our cosmic neighborhood were so varied and complex, then the magnetic environments around extrasolar planets might be equally diverse. Understanding planetary magnetism became crucial for assessing the habitability of worlds around other stars. Throughout their journey across the solar system, both Voyager spacecraft carried infrared instruments that measured temperatures across a range of environments more extreme than anywhere found on Earth. From the volcanic furnaces of Io to the cosmic deep freeze of interstellar space, these temperature readings revealed a universe where matter existed under conditions that challenged the very definition of hot and cold. Io provided the most dramatic temperature extremes in the solar system. Voyager's infrared detector measured volcanic hotspots reaching 3,000 degrees Fahrenheit, temperatures hot enough to melt copper instantly and rival the heat found in steel foundries. These weren't gentle lava flows like those found in Hawaii. They were explosive eruptions that launched molten sulfur hundreds of miles into space at temperatures that would vaporize most metals. But just miles away from these volcanic furnaces, Io's surface temperatures plunged to minus 260 degrees Fahrenheit, creating one of the most extreme temperature gradients ever measured on any world. The volcanic regions were literally red-hot islands of molten rock surrounded by landscapes cold enough to freeze carbon dioxide solid. Stepping from a volcanic plain to a cold region on Io would be like walking from the inside of a blast furnace directly into liquid nitrogen. Europa presented a different kind of thermal mystery. Despite being farther from the sun than Io, Europa's subsurface ocean remained liquid at temperatures around minus 100 degrees Fahrenheit, still cold enough to kill any Earth life instantly, but warm enough to maintain the largest body of liquid water in the solar system outside of Earth. Tidal heating from Jupiter generated just enough energy to keep this vast ocean from freezing solid. Saturn's moon Titan showed how atmospheric greenhouse effects could warm a world far from the sun, despite receiving only 1% of the sunlight that Earth enjoys. Titan's thick atmosphere trapped enough heat to maintain surface temperatures around minus 290 degrees Fahrenheit. While still brutally cold by Earth standards, this was actually warm enough for liquid methane to exist, creating hydrocarbon lakes and weather systems impossible anywhere else in the solar system. The outer planets themselves revealed temperature extremes that defied easy explanation. Neptune, despite being 30 times farther from the sun than Earth, had atmospheric temperatures that were almost identical to those found on Uranus, which was much closer to our star. Neptune's internal heat source was so powerful that distance from the sun became almost irrelevant to its atmospheric temperature. Voyager's temperature measurements of planetary ring systems revealed another thermal puzzle. Saturn's rings showed complex temperature variations that had nothing to do with solar heating. Some regions of the rings were warmer than others due to particle collisions and electromagnetic heating, creating thermal patterns that constantly shifted as the rings evolved. The rings were essentially cosmic heat engines, powered by gravitational and electromagnetic forces. The most extreme cold measurements came as Voyager 1 entered interstellar space. The cosmic background temperature in the void between stars measured just 4 degrees above absolute zero, minus 455 degrees Fahrenheit. At these temperatures, almost all matter except hydrogen and helium would be frozen solid. This was the thermal environment that dominated most of the universe, where the absence of nearby stars created conditions of almost perfect cold. But even in interstellar space, Voyager detected unexpected temperature variations. Shock waves from ancient supernova explosions had heated some regions of interstellar gas to millions of degrees, creating bubbles of incredibly hot plasma floating in the cosmic deep freeze. These hot regions were so tenuous that a thermometer would still read near absolute zero. But individual gas atoms were moving at speeds equivalent to millions of degrees of temperature. The spacecraft also measured the thermal effects of magnetic fields throughout the solar system. Charged particles trapped in planetary magnetospheres were heated to temperatures of millions of degrees through magnetic acceleration and compression. Jupiter's radiation belts contained particles with effective temperatures higher than the surface of the Sun, even though the overall environment was still the cold vacuum of space. These temperature measurements revealed that the universe was filled with thermal extremes that made Earth's climate seem remarkably mild and stable. The range of temperatures found just within our own solar system spanned more than 3,000 degrees, from volcanic hotspots to the cosmic background temperature, creating environments where matter existed in states impossible to reproduce in terrestrial laboratories. 45 years after leaving Earth, both Voyager spacecraft continue racing through the cosmic darkness, their nuclear hearts still beating steadily as they transmit humanity's first reports from interstellar space. These two small machines have fundamentally transformed our understanding of the solar system and our place within the vast universe that surrounds us. The discoveries made during Voyager's grand tour read like science fiction that became reality: active volcanoes on alien moons, global oceans hidden beneath ice, hexagonal storms larger than Earth, twisted magnetic fields, and ring systems that sing with electromagnetic music. Each world visited revealed surprises that forced scientists to rewrite textbooks and expand the boundaries of what seemed possible in planetary science. Perhaps the most profound discovery was that our solar system is far more dynamic and alive than anyone had imagined. Instead of finding dead worlds orbiting in eternal silence, Voyager revealed a cosmic ecosystem where moons erupt with geysers, atmospheres circulate with supersonic winds, and magnetic fields create invisible highways for charged particles. The outer planets proved to be entirely different kinds of worlds, operating by their own physical laws. The journey demonstrated humanity's remarkable ability to extend its senses across impossible distances through robotic exploration. Voyager's instruments became our eyes and ears in the cosmic wilderness, allowing us to see storms on Neptune, hear radio waves from Jupiter, and witness the birth of new worlds. These machines became extensions of human consciousness, reaching into the previously unknowable darkness. Each spacecraft carries the golden record, humanity's message to any alien intelligence that might find these cosmic bottles cast into the interstellar ocean, long after Earth has forgotten these missions. Voyager 1 and 2 will continue sailing between the stars as ambassadors from our small planet, carrying greetings, music, and images that capture the essence of human civilization. The data streaming back from both spacecraft continues to revolutionize our understanding of the boundary between our solar system and interstellar space. These measurements help scientists understand how our sun interacts with the galaxy around it, revealing processes that occur around every star in the Milky Way.
The day the last neutrino from the Big Bang is caught will not change the world. No cities will rise or fall, no empires will tremble, but it will mark a moment in which humanity, born from star ash and folded proteins, will have traced its origin not just to the stars, but to the silence that came before them. Before stars burned, before atoms clung together, before even the first light was free to move. The universe was a smooth, expanding sea of particles and energy, dense, hot, and opaque. Time had already begun, but it meant nothing yet. No rhythm, no recurrence, no record. In those first fractions of a second, the universe was governed by a furious symmetry, forces indistinguishable, matter and antimatter evenly matched. But perfect balance cannot last. A slight asymmetry, perhaps born from quantum indeterminacy. Perhaps something deeper tilted the scale. For every billion pairs that annihilated each other, one particle remained. That 1 in a billion excess became the seed of everything to come. Inflation came next. Not the inflation of economics or balloons, but a roaring expansion of space itself, faster than the speed of light, driven by an energy we still do not understand. What had been the size of a proton exploded into something many orders of magnitude larger in less than a blink. That expansion was not into space, it was of space. Time stretched. Fluctuations, tiny variations in quantum fields were frozen and magnified, becoming the template for all later structure. When inflation ended, energy transformed into matter and radiation. The universe cooled. Quarks combined into protons and neutrons. Neutrinos decoupled and fled freely into the void. A few minutes later, nuclei formed in a process called Big Bang nucleosynthesis, giving rise to helium, deuterium, and traces of lithium. But it would be nearly 400,000 years before the universe became transparent. During that age, photons scattered off free electrons in a blinding fog. Only when the universe cooled enough for electrons to bind with nuclei forming neutral atoms did light break free. That first light still echoes around us today, redshifted by expansion into the cosmic microwave background. It is not background noise. It is the oldest light we can see. The afterglow of the birth of form. Galaxies did not appear at once. Matter was clumped unevenly by inflation's frozen fingerprints. Gravity pulled at those denser regions, amplifying their imbalance. Gas collected. Over millions of years, it cooled and collapsed into the first stars. These stars were not like the ones we know. They were vast and short-lived, burning quickly and dying in supernovae that forged the first heavy elements: carbon, oxygen, iron, and seeded space with ingredients for new generations. Among those later generations of stars, some gathered into swirling disks. Around certain stars, dust and rock orbited and collided, sticking and shattering in cycles that eventually produced planets. On at least one of those planets, chemistry learned how to copy itself. Then it learned to remember. Then to question. But the expansion never ceased. Even now, galaxies drift apart not through motion, but because space itself stretches between them. The greater the distance, the faster the separation. It is not speed in the usual sense. It is geometric unraveling, and embedded in that unraveling is a future we barely understand. We measure this expansion through redshift, the lengthening of light waves from receding galaxies. The farther a galaxy, the redder its light. It is as though the universe breathes, and in that breath we find direction. From redshift we calculate the Hubble constant, a value that defines how fast the universe expands at different times. But even here, precision unravels. Different methods give slightly different answers. The early universe and the nearby cosmos tell conflicting stories. We do not yet know why. Still, the fact of expansion is beyond doubt, and that fact carries consequences. It tells us the universe had a beginning, that it is not static, that it changes, that it may end. Yet perhaps even more profoundly, it tells us this: the past is not merely before us. It is inside us. Every atom in every bone, every drop of water, every breath of air carries a lineage that reaches back to those first lightless moments. To remember is not only a function of mind, it is the act of existing at all. The first stars died to make complexity possible. Their remnants became the galaxies we inhabit, and those galaxies, in their swirling motion and gravitational dance, began to shape the vast architecture of the cosmos. Filaments, voids, walls of clustered light, a structure drawn from chaos by time, mass, and the gentle tyranny of gravity. But even this structure is temporary. Expansion continues. Dark energy, once negligible, now dominates the evolution of space. The acceleration it causes means that distant galaxies will, one day, drift beyond our observable horizon. They will vanish not because they move faster than light, but because the space between us stretches too fast for their light ever to reach us. The night sky, now thick with stories, will thin. Over eons, fewer galaxies will be visible. Eventually, all will disappear, leaving only the local group, bound together by mutual gravity. The visible universe will shrink not in size, but in content. And those who live then, if any do, may not be able to guess what we know now, that they are part of something vastly more ancient and wide. The life of a star begins in cold silence. In regions of space where gas and dust gather thickly enough, gravity starts its slow work. At first there is no light, only contraction. Atoms are pressed closer together, and as density increases, so does heat. What begins as a diffuse cloud becomes a core of rising temperature and pressure. The star-to-be hides inside, wrapped in veils of dust, invisible to human eyes but radiating softly in infrared. Eventually, fusion ignites. Hydrogen nuclei fuse into helium, releasing vast amounts of energy. The balance is struck, gravity pulling in, fusion pushing out. A star is born not in a flash, but in a sustained fire that can last for billions of years. Its light is not flame. It is the release of mass, converted to energy, by the simplest and most ancient process in the universe. Our own sun, modest in size, lives in this stable phase now. It has burned for over 4 billion years and will continue for about as long again. But stars are not immortal. Their fate is written in their mass. Small stars burn slowly, sipping their hydrogen reserves. They grow old with great patience and end their lives gently, cooling into dim remnants called white dwarfs. Large stars burn fast and die young. Their cores collapse. Their outer layers explode. A supernova is not merely a death. It is a crucible. In that final violence, heavier elements are forged: iron, gold, uranium, the building blocks of planets, of bodies, of thought. Some stars, in their dying collapse, go further. If the remaining mass is great enough, even the pressure from neutron degeneracy, nature's desperate resistance to collapse, fails. The star becomes a black hole, not an object, but a region of space so warped that not even light can escape. Time slows near it. Space curves inward. What falls in does not return. And yet black holes may spin, glow, and merge. They are paradoxes that exist, and they are everywhere. At the centers of galaxies, including our own, lurk supermassive black holes millions to billions of times the mass of our sun. Their origin is uncertain. Did they grow from stellar seeds, feeding slowly for eons, or were they born massive? In the early chaos of the first galaxies, we do not know. But we do know they shape the galaxies around them. Their gravity governs the motion of stars. Their outbursts regulate star formation. They are not merely destructive. They are sculptors. When galaxies collide, and they do, frequently over cosmic time, their stars pass mostly untouched. The distances between stars are too vast, but their gas clouds crash, compress, and trigger starbursts. New stars form in the wake of chaos, and often, the central black holes of each galaxy begin a slow dance of their own, spiraling closer over millions of years until, at last, they merge. The energy released in such an event ripples across space-time itself, gravitational waves. These waves stretch and squeeze the very fabric of the cosmos, passing through everything, including us. We have only recently begun to detect them. The first confirmed observation of gravitational waves, in 2015, came from two black holes merging over 1 billion light-years away. The signal lasted less than a second, but it told a story older than humanity. Instruments like LIGO and Virgo, tuned to impossibly small vibrations. Now listen constantly. The universe is no longer silent. Not all stellar remnants are so final. Some collapse into neutron star spheres no wider than a city, but with masses greater than the sun. Their matter is so compressed that a teaspoon of it would weigh billions of tons. Some spin rapidly, beaming radiation like cosmic lighthouses, pulsars. Others merge, creating kilonovae and forging the heaviest elements in the periodic table. Even in death, stars give. But as these grand narratives unfold, a quieter process continues: the slow aggregation of matter into galaxies, the coalescence of gas into disks, the spiraling dance that forms stars again and again. Our galaxy, the Milky Way, is one among hundreds of billions. It is a barred spiral, its arms winding in graceful arcs. It orbits its own center every 200 million years, a single galactic year. We are now in the 22nd such orbit since the Sun formed. In a few billion more years, the Milky Way will merge with its neighbor, the Andromeda Galaxy. The skies will shift. New stars will form. The structure will change, but gravity will continue its work. The universe does not mind change. It embraces it. And amid this vast dynamic system, there are quiet places: solar systems, planets, oceans, perhaps even mines. Outposts of calm in the storm. Local awakenings within a cosmos that, for most of its life, has been unconscious. We are not outside this story. We are one of its brief expressions. The atoms that carry our thoughts were forged in stars now dead. The iron in our blood, the calcium in our bones, the gold we wear, all born in stellar collapse. We do not orbit the universe like passengers. We are made of it. To understand that is not to diminish our importance. It is to ground it in something real. We are not flukes of dust, nor divine exceptions. We are what the universe does when it has time, space, and memory. A pattern, subtle yet persistent, haunts the universe. Galaxies spin, but not as they should. Their outer stars orbit too fast, as if pulled by invisible strings. Clusters of galaxies hold together more tightly than their visible mass allows. Light bends around them, distorted by gravity that should not be there. These are not flaws in data. They are fingerprints of something unseen. What we call dark matter is not a shadow or absence. It is presence without interaction. It does not glow, absorb, or reflect. It reveals itself only through gravity, its quiet pull shaping the dance of galaxies. The structure of the cosmos. It is 5 times more abundant than ordinary matter, yet its nature remains unknown. It might be particles that do not interact with light. It might be a field, a modification of gravity, or something entirely outside our frameworks. For decades, detectors have waited in deep mines, shielded from cosmic rays, hoping to catch a passing dark matter particle. None has yet arrived. Particle colliders have searched for hints of exotic components, signs of supersymmetry, or extra dimensions. Still, silence. And yet, the gravitational evidence accumulates. Whatever dark matter is, it binds the cosmos. Just as mysterious is the force that pushes galaxies apart. Unlike gravity, it repels. Unlike matter, it spreads uniformly. In the late 1990s, observations of distant supernovae revealed that the universe's expansion is not slowing down, as once assumed, but accelerating. Something is counteracting gravity on the largest scales. This accelerating force is called dark energy. It constitutes nearly 70% of the universe. Unlike dark matter, it does not cluster. It stretches space itself, faster and faster, with time. If this expansion continues indefinitely, galaxies beyond our local group will recede beyond our view. Over trillions of years, even the radiation they once emitted will become undetectable. The observable universe will grow emptier. The nature of dark energy is unknown. It could be a constant property of space, a cosmological constant, as Einstein once proposed. Or it could be a dynamic field, like the inflaton that drove cosmic inflation. Some suggest it may decay, change, or even reverse. Its behavior shapes not just the future of the universe, but the limits of what we can know. Together, dark matter and dark energy form the invisible scaffolding and wind of the cosmos. Ordinary matter, the stars, planets, and people, is a thin film stretched across these deeper layers. And yet, from that thin film, awareness has emerged. It is one of the strangest truths of cosmology that what is most abundant is least understood, and what is rare is capable of understanding. But perhaps rarity is not weakness. Perhaps it is precisely the contrast that gives it power, a flicker of clarity in a sea of mystery. Some theories propose that dark matter could decay, slowly, over unimaginable spans of time. If so, the structure it supports may dissolve. Others suggest it might interact under certain conditions, revealing new forces or particles. In some models, dark energy might trigger a big rip, where expansion accelerates to the point that galaxies, stars, planets, and even atoms are torn apart. Alternatively, the expansion could slow. If dark energy changes sign, gravity could regain dominance. The universe might recollapse in a big crunch, or oscillate in cycles eternally expanding and contracting. These are not just speculative endings. They are tests of the laws we live by. But not all endings are explosive. There is also the possibility of a heat death. If expansion continues forever and energy spreads evenly, the universe will approach thermodynamic equilibrium. No gradients, no usable energy, no change. Entropy will have reached its maximum. The universe will not die in fire, but in stillness. Against this vast, unfolding canvas, every observation is a protest against ignorance. Each new telescope, each particle detector, each deep space probe is an act of hope, not just that we can learn, but that learning matters. We map the cosmic web, chart the redshifts of distant galaxies, model the invisible components of mass, not because the universe demands it, but because something in us does. To know is to push back against the dark, not to eliminate it, but to see it more clearly. The quest for understanding does not promise safety or control. The universe does not bargain, but it does offer coherence, a way to stitch together the fleeting and the vast, the personal and the physical, into something that feels like meaning. And meaning perhaps is not found. It is made through connection, recognition, and wonder. In the patterns of galaxies, in the silence between the stars, in the questions we ask and cannot yet answer, there is something enduring, not knowledge alone, but the will to seek it. The cosmos may be ruled by forces we cannot touch or see, but it also contains the mind that asks why. That, in itself, may be the rarest phenomenon of all. A molecule, nestled in a droplet of warm, shallow water, wobbles into a shape that copies itself. Not perfectly, but enough. The copy too folds, twists, and begins its own repetition. Errors creep in, some useless, some fatal, some fruitful. So begins a pattern, not of stars or galaxies, but of behavior, of replication, competition, emergence. Over time, these molecular dancers grow more intricate. They form chains, membranes, strategies. And one day, in a place long lost to time, they become aware. Life, unlike stars, is not inevitable. It does not fall out of the laws of physics in the same way as gravity or fusion. It requires narrow conditions, balance, instability, time, and energy gradients that persist just long enough for matter to organize into memory. And yet, it happened. At least once. On a rocky planet, circling a modest star, in the spiral arm of a galaxy that is one among many. This emergence turned matter into meaning. The laws of physics did not change, but a new kind of order arose, one not dictated by entropy, but by selection. Organisms appeared, evolved, adapted. Some grew eyes to see, some fins to swim, some wings to glide between forest canopy and sky. But one lineage grew minds not merely to react, but to remember across generations. To shape the world not with claws or venom, but with thought. Consciousness is not yet fully understood. Some believe it arises from complexity, from enough neurons firing in the right patterns. Others argue it may be a fundamental property of matter, waiting for the right structure to amplify it. Perhaps it is a byproduct, perhaps a purpose. But whatever its nature, consciousness does something remarkable. It reflects. It builds inner models not only of the present, but of past and future, of self and other. It becomes narrative. From the earliest cave paintings to radio telescopes scanning the sky, life has used story to remember, to share, to stretch beyond its own limits. Physics gives us light and heat. Consciousness gives us questions. What is time? Why does anything exist at all? Are we alone? The search for extraterrestrial intelligence is not merely curiosity. It is loneliness scaled to the size of galaxies. We have scanned the skies for signals, sent probes across the solar system, and launched metal records aboard spacecraft that may drift for billions of years. We have found no answer yet, but the silence itself is data. If intelligence is rare, perhaps it is precious. If it is common, perhaps we are early. The anthropic principle suggests that the universe must allow for our existence, because we are here to observe it. But some interpretations go further. Perhaps there are many universes and infinite multiverse with varying laws and constants. In most, life is impossible. In a few, life stirs. We live in one of those few. This idea, while impossible to test directly, reshapes how we think about probability, purpose, and design. The fine-tuned constants of nature, the strength of gravity, the mass of the electron, the rate of expansion may not be tuned at all, but sampled. We inhabit one roll of an infinite dice, but even if there is only this universe, the fact of our presence is astonishing. The particles that make up your hands, your thoughts, your voice, have traveled across stars and epochs. They formed in supernovae, drifted through interstellar space, were pulled into Earth's gravity, and finally joined into patterns that dreamed, feared, and hoped. You are not outside of nature. You are its unfolding. Philosophers have long debated whether consciousness is an emergent property or a fundamental substance. Some traditions speak of mind as primary, with matter as its shadow. Others reverse the lens entirely. In modern physics, questions of observation tangle with quantum theory. Does the act of measurement collapse a wave function? Does awareness play a role in shaping reality? These are not settled debates, but their persistence shows something important, that knowing we know changes the game. We build models of the world, and those models affect the world. A theory of gravity launches satellites. A theory of atoms cures disease. A model of ecosystems reshapes agriculture. Our inner abstractions reshape the outer physical world. Consciousness is not passive, it loops. And in that looping, new questions emerge. What obligations arise from awareness? What do we owe the future, the planet, each other? Evolution did not require ethics, yet here we are, asking how to live. Morality may not be written in the stars, but it is written in us, in mirror neurons, in language, in the long arc of cooperation. The rise of artificial intelligence brings further questions. Can machines become conscious? What happens when we create minds unlike our own? Do they inherit our values, or rewrite them? If we are a spark of awareness in a vast dark, should we try to kindle other sparks? Perhaps the most radical possibility is not that consciousness is rare, but that it is everywhere, in forms we cannot recognize. Perhaps intelligence shaped by other biochemistries, other histories, other senses, would be unrecognizable not because it is absent, but because we are blind to it. Whatever the case, the emergence of thought marks a turning. Before life, the universe changed only by natural law. After thought, it began to change by choice, and with that choice comes responsibility. A machine the size of a small car sits silently beneath kilometers of ice in Antarctica, waiting for neutrinos. It does not see them directly. Instead, it watches for the rare flash of light when one of these ghost particles, billions of which pass through your body each second, happens to collide with an atom. This detector, called Ice Cube, is part of a global effort to look deeper, not just into space, but into the patterns of reality that underpin everything we call the universe. There are limits to sight, limits to hearing, limits to every sense evolved in the warm, slow turbulence of Earth's air and oceans. But instruments expand those senses. Radio telescopes hear hydrogen singing across light years. Gravitational detectors feel the trembling of space-time itself. Spectrometers analyze the chemical fingerprints of distant planets. Each tool translates something invisible into something knowable. We are no longer confined to a single planet's perspective. Probes have mapped the weather of Jupiter, tasted the ice of Enceladus, walked the dusty plains of Mars. Telescopes have captured light that began its journey before our solar system formed. We have measured the temperature of empty space and found it not to be zero, but a gentle whisper of warmth, a relic from the moment light became free. As technology grows, so does the horizon of what can be asked. Questions that once belonged to metaphysics now belong to physics. Time, for instance, is not an absolute river flowing from past to future. It is a dimension, shaped by gravity and velocity. Clocks tick slower in gravity wells. Simultaneity dissolves. In the equations of general relativity, time and space are part of a single fabric, curved by mass, twisted by rotation. But this view is classical. At quantum scales, reality becomes less smooth. Particles pop into and out of existence. Probabilities replace certainties. Entanglement allows particles to affect one another instantaneously, across arbitrary distances. Measurement becomes participation. And between these two views, relativity and quantum mechanics, there is still no final unity. The search for a theory of everything is not merely academic. It is a quest to reconcile the large and the small, the smooth and the jittery, the cosmic and the granular. String theory, loop quantum gravity, emergent space each offers glimpses, none yet complete. Some suggest space-time itself is not fundamental, but emerges from deeper informational structures. That space may be the shadow of relationships, not a stage upon which they play out. And then there is the simulation hypothesis, the idea that reality itself might be computational, that consciousness arises within a system designed not by gods or nature, but by future beings capable of generating entire universes as code. The question is not whether this is true, but what it means that it can even be asked. That physics, at its limits, begins to resemble information theory. That black holes, once thought to erase data, might in fact encode it on their event horizons. That entropy, information, energy, and time are more entangled than we yet understand. But perhaps the greatest mystery is not out there. It is in the act of understanding itself. Why should a universe governed by indifferent laws produce a creature capable of awe? Why should a pattern of carbon and calcium reflect on the infinite? Perhaps consciousness is not an accident. Perhaps it is how the universe awakens to itself, not once, but many times, in many forms, across time and space. The future, if we endure, will not resemble the past. Earth will not always be habitable. The sun will expand, then die. Even if we travel to other stars, entropy marches on. Civilizations may rise, fall, forget, and begin again. But the knowledge we build now can echo forward, etched in materials, in signals, in engineered life. Not immortality, but continuation. What we choose to preserve may outlast us. What we choose to understand may empower what comes next. And if we send messages into the dark recordings of our languages, our music, our questions, we do so not for reply, but to mark that we were here, that we looked outward, that we asked. We may never escape the ultimate silence. Every star will die. Every black hole will evaporate. If the universe ends in cold diffusion or final compression, there may be no one left to remember. But in the time we have, we remember, we listen, we wonder. And that perhaps is enough.
There are moments when the night appears too vast to understand, and yet too intimate to ignore. The eye, born from stardust, finds itself compelled to return that gaze. But the stars offer no answers. They shine not to guide us, but because they must. Still, we ask. Still, we build mirrors of glass and algorithms to decode what lies between them. The James Webb Space Telescope did not arrive as a symbol, it arrived as a silence, slowly unfolding in the cold vacuum, petal by petal, mirror by mirror, launched not to replace, but to extend what our sight could become. Not merely a machine, but a question sharpened to a point of light. And light is all it needs. The kind that began its journey when Earth had no cities, no names. The kind bent by galaxies, stretched by cosmic expansion, softened by time. It is not the present the telescope sees, but a museum of ancient fire. The telescope, orbiting far beyond the moon, bathes in shadow. It carries no flashlight. Its mirrors are polished to reflect the oldest light, the kind no eye has seen. Not the sharp blue of a nearby star, but the long red whisper of something impossibly far. It looks not into space, but into time itself. As its gold-plated segments aligned, they captured not a single image, but a depth, each dot in its field a galaxy. Not a star, a galaxy, hundreds of billions of stars in every speck, structures bent into arcs by gravity so strong, they twist light like silk. What we see is not what is. What we see is what was, revealed by the time it takes to arrive. Among those arcs and fragments are galaxies so old, they defy expectation, formed when the universe was young and raw, less than 500 million years past its birth. They are compact, rich in stars, strangely mature. Their presence unsettles timelines. If these galaxies existed so soon after the beginning, then our models must stretch to accommodate them. They are not errors. They are revelations. Yet revelations bring discomfort. The data does not confirm, it provokes. Galaxies shine when they should not yet exist. Their chemistry is too advanced. Their structures too settled. We are not disillusioned. We are invited to rethink. Perhaps the formation of galaxies was more urgent than imagined. Perhaps the early universe was not uniform, but wild with possibility. Perhaps our assumptions of symmetry and gradual structure must yield to new models, ones where turbulence, gravity, and dark matter assembled stars faster, brighter, denser than expected. This is not a crisis. It is the work to revise, not resist, to see the image not as disruption, but as instruction. The telescope shows us a universe not that betrayed us, but that moved faster than we anticipated. Its silence is not a refusal, it is a gift of deeper questions. And we, tethered to a small planet under an aging star, now witness the light of things born when the cosmos itself was a child. To see them is not just to see history, it is to meet the boundaries of our understanding and to walk into them willingly. A mirror turned outward also turns inward. As the James Webb Space Telescope reached deeper into the sky, it inadvertently drew us into a closer encounter with ourselves. For all its precision and distance, the most arresting images it returned were not of alien terrain or spectacular collisions, but of light curved, reddened, ancient, light that had crossed epochs to find a home on a golden mirror. Among these signals were arcs of light wrapped around invisible centers. Einstein had predicted it long ago that gravity could lens light, bend it not metaphorically but geometrically. Here it was, visible and undeniable cosmic lenses magnifying the unreachable. Behind them, galaxies swam into view that would otherwise remain hidden. They shimmered like ghosts, brought into existence by the gravity of clusters layered between us. Through these lenses, the telescope captured galaxies whose ages defied our calendars. Their redshifts, markers of distance and time, suggested they had formed mere hundreds of millions of years after the Big Bang. And yet, they bore the signatures of maturity, heavy elements forged in stars, structures suggesting rotation and gravity-bound systems. Not chaos, but complexity. This prompted a quiet discomfort among cosmologists, not because it challenged the data, but because it whispered that the universe may have grown up faster than our equations had allowed. If galaxies of such mass and richness existed so early, then the seeds of structure must have taken root in even deeper darkness. Perhaps inflation planted them more effectively than we thought. Or perhaps something in our modeling of early star formation, of the interaction between gas and gravity, needed reimagining. And so, the telescope became not just an eye, but a teacher. It asked, without words, whether our explanations were too tidy, too linear. It showed us that the cosmos is not obligated to match our expectations. The models exist to interpret the sky, not dictate it. Yet even as the early universe offered its riddles, the nearer cosmos answered with texture. Nebulae bloomed in infrared, revealing layers of gas and dust invisible to previous instruments. Structures once blurred became sharp. Birthplaces of stars glowed with the residue of ignition. We saw not just forms, but processes. These stellar nurseries, once only hints, now unfolded in cascading detail. The pillars of creation no longer hid behind shrouds, they glowed, pierced by the very light they had birthed. Regions of turbulence, where gravity struggled against radiation, painted pictures of the tension from which suns are born. But perhaps most profound were the spectra. Stripped of beauty, they offered the raw fingerprints of atoms. In them, scientists found traces of water vapor, carbon dioxide, and methane, not just in nebulae, but in the atmospheres of exoplanets orbiting distant stars. These were not just points of light. They were places, with weather, with chemistry, with potential. A planet hundreds of light years away, invisible to any eye, suddenly revealed what clung to its skies. The composition of distant worlds, once a fantasy, had become data. And with that, the line between astronomy and biology thinned. The search for life no longer lived only in hopeful signals or surface images. It now had molecular paths to follow. The telescope, in its quiet task, made the improbable intimate. It reminded us that light, no matter how old, still speaks. That distance does not erase detail, and that from our small perch, we are now listening more carefully than ever before. In the realm of the very distant, the very small often holds the most sway. Between galaxies and nebulae lies a scaffolding that light alone cannot reveal, a hidden web shaped by gravity, populated by the invisible, and animated by laws yet unfinished. The telescope does not see this web directly. It traces it through absence, through distortion, through the motions of what should not move the way it does. Every image that reaches its mirror is touched by dark matter, this unseen substance, outweighing the ordinary by 5 to 1, clings to galaxies like a skeleton beneath the flesh of starlight. Without it, those galaxies would not hold together. Their stars would fly apart under their own speed. With it, structure endures. The telescope's images, then, are not merely of light, they are portraits shaped by shadow. The gravitational lensing of distant galaxies maps the pressure points of dark matter. Where light bends, mass resides. The more dramatic the arc, the heavier the weight behind it. And so, by observing distortion, we glimpse the silent architecture of the cosmos. But gravity is not the only force at play. The telescope peers into wavelengths designed to escape interference. It sees through veils of dust that once cloaked entire regions from view. That dust, forged in the death of stars, is both an obstruction and a womb. It hides and reveals in equal measure. What Webb sees are not just clearer pictures, but different truths. In the early universe, it finds galaxies forming with extraordinary compactness. Starburst galaxies rushing through their supply of gas at 10, 20, 50 times the rate of the Milky Way emerge in abundance. These cosmic forges, seen at redshifts higher than 10, should not yet exist by some models. And yet they glow defiantly, their ultraviolet light stretched into infrared by the expansion of space. Within these galaxies, the telescope begins to uncover chemical signatures once assumed too complex for such an early time. Elements heavier than helium, born in the hearts of massive stars, appear in quantities that imply a rapid recycling of stellar generations. Death and rebirth on cosmological timescales far faster than we expected. The presence of such metals this early means stars were forming, dying, and enriching their environments at a breathtaking pace. It reshapes our understanding of galactic metabolism. It forces us to ask whether the timeline of the first supernovae, the emergence of black holes, and the ionization of the intergalactic medium needs to be rewritten. Ionization, the process by which neutral hydrogen was torn apart into protons and electrons, is one of the great transitions in cosmic history. The telescope now sees its traces more clearly. It captures the glow of galaxies as they punch holes in the neutral fog, letting light travel freely for the first time since the cosmic microwave background was born. This age, the epoch of Ryanization, is no longer an abstraction. It is being mapped, layer by layer, galaxy by galaxy. And in doing so, we edge closer to answering the most elusive question: how did the cosmos turn from darkness to complexity? Not with a single light, but with a storm of them. Not with gradualism, but with convulsion. The early universe, once thought to be sleepy, appears instead like a forge, loud, crowded, raw. Its tempo has changed, its rhythm quicker, its story less linear and more emergent. And through it all, the telescope remains a listener, not to sound, but to structure, not to noise, but to nuance. Each photon it catches is a vote for reality over theory, a reminder that the universe is under no obligation to mirror our expectations. Beyond the veil of time and radiation, there are worlds, not imagined, but measured, not mythic, but spectral. The James Webb Space Telescope does not photograph oceans or mountains. It catches atmospheres. It reads starlight that has passed through the breath of alien planets, and in that thin filtering detects what lingers in the air. Water vapor, methane, carbon dioxide, molecules once measured only on Earth now shimmer in the light of stars hundreds of trillions of kilometers away. They drift across gas giants far closer to their suns than Jupiter dares orbit. They settle into skies of planets larger than Earth, but smaller than Neptune. They mark conditions, not proof, but potential. These are exoplanets, once speculative, now catalogued by the thousands. Their orbits dim stars by a fraction, and from those dimmings we measure size, period, distance. Webb adds the missing piece: chemistry, by watching a planet transit its host star and capturing the starlight that skims its atmosphere. The telescope unveils the fingerprints of gases, even at whisper-level concentrations. In one such world, a gas giant orbiting tightly to a dim red sun, Webb detects carbon-bearing molecules with clarity no previous mission could achieve. The spectrum flattens, then curves, revealing a chemical complexity that stirs curiosity. This is not life, but it is not lifelessness either. It is the context from which life might emerge. It turns its eye to TRAPPIST-1, a system of 7 rocky planets, some of them poised in the star's habitable zone. It watches as these Earth-sized worlds eclipse their cool sun. Their signals are faint, fragile, but Webb persists. It catches hints of carbon dioxide in one, perhaps water in another. The atmospheres are thin, the noise high, but the story begins. These are not photographs to frame, they are codes to parse. What Webb gives us is not certainty, but direction. It points to the chemical conditions under which biology might arise. It does not promise discovery. It opens the door through which discovery might walk. But the telescope also reminds us that habitability is not a binary. It is a spectrum. It depends on the dance between starlight and atmosphere, between magnetic fields and geological cycles, between temperature and time. Earth is not the only solution. It is a single fortunate variation among many possibilities. We now understand that life, if it exists elsewhere, may not mirror us. It may not walk or think or build. It may flicker as microbial shadows under ice. It may breathe ammonia, not oxygen. It may never dream, but it may endure. This is the beauty of Webb's revelations. It does not anthropomorphize the cosmos. It humbles us. It removes the presumption of centrality and replaces it with participation. We are not the measure of the universe's creativity. We are one of its outcomes. And so, in each spectrum captured, We see less of ourselves and more of the possible. Each distant world is not an echo of Earth, but a variation in the melody of matter. Some may be barren, some may bloom, we do not know. But the knowledge that we can even ask, that we can even begin to test, marks a shift in our place. For the first time in history, life on Earth is no longer merely wondering. It is listening. It is measuring. It is looking not outward for confirmation, but outward for connection. The farther we look, the stranger the questions become. In the deep field images of the James Webb Space Telescope, the universe stretches into a canvas of paradox, brilliant with clarity, yet haunted by limits. Not the limits of technology, but the deeper ones, etched into the fabric of existence itself. For all we can see, there are boundaries we cannot cross, and behind them may lie the reason we can see at all. Cosmology has always walked the knife's edge between physics and philosophy. Now, with eyes sharper than ever, it begins to ask whether reality is what it appears to be or whether it has always been a construction, not a fabrication, but a structure so elaborate it deceives even the senses that probe it. Some voices whisper of a simulated universe, not as metaphor but as model. If the cosmos behaves like a computation, if its constants are finely tuned and its information conserved with perfect fidelity, then perhaps we are embedded in something designed by nature, by intelligence, or by something we cannot name. This is not a claim, it is a question. And Webb, though silent on such speculation, adds weight to its possibility. Because in seeing deeper, we find more precision, not more randomness. The early galaxies, once assumed to be chaotic and primitive, reveal order and complexity, the patterns of star formation, of element distribution, of gravitational assembly. They all cohere too well. It is as though the universe was ready for complexity from the beginning. The cosmic microwave background, the afterglow of the Big Bang, is uniform to 1 part in 100,000. The equations that predict its distribution work. They work too well. Inflation theory, dark matter, dark energy, they form a model that explains nearly everything. And yet, none of these components are directly understood. If the universe is a simulation, then perhaps the speed of light is not just a limit, but a boundary condition. Perhaps quantum uncertainty is not a bug, but a feature. Perhaps black holes are firewalls, points where information is compressed, not lost. These are not answers, but provocations, born not of science fiction, but of mathematics and physics pushed to the edge. Webb cannot confirm or deny any of this, but it fuels the question with every unexpected detail. It confronts us with the raw fact that the universe has rules, and that we are capable of uncovering them. That very capability demands reflection. What kind of reality allows its creations to comprehend its scaffolding? If this is not design, then it is poetry of the highest kind, a universe that, without intent, gives rise to meaning. If it is design, then the implications exceed any theology, not because we are special, but because we are not. We may be simulations within simulations, observers within observers, shadows cast by deeper machinery. Yet meaning persists, regardless of foundation. Whether real or rendered, our questions are real. Our wonder is real. The telescope, unfeeling and precise, becomes a vessel for that wonder. It gathers data, but we assign the weight, we feel the astonishment. We press the questions further. The night sky is no longer just a map of stars. It is a language, a system, a challenge. And in decoding it, we learn not just what the universe contains, but what it permits us to become. In the end, what Webb reveals is not only what is there, but what is possible. A universe pregnant with structure, with symmetry, with surprise. A reality where time unfolds not as a straight path, but as a spiral returning again and again to the same questions, each time with sharper tools, deeper thought, and greater humility.